All right, yesterday we said we have, what did we say, 3 different ways we could find f prime of 1. Remember that? Okay, matter of fact, maybe let me pull this up. It's been crazy this morning and I'm way behind myself. All right, so, All right, so yesterday we had this, we said how many ways can we find f prime of 1, right? And one way was what? Graph it and do a tangent line, right? What was another way? Zoom, pick 2 really close points, right? And put in a 1 and a 1.01. Okay, what was the third one? The definition, which is up on the board, so we're all very, very clear what we're talking about. Definition of the derivative, or limit definition of the derivative is sometimes called, is the long way, right? That's working it out the long way, right? That's the definition of the derivative, okay? Is going through that whole limit process, okay? So we said those were the 3 ways. Well, we now, at the end of the period, we added another one. What was it? The power rule, right? Or just a shortcut, just a derivative rule. Now that's different, okay? So I don't know what the best way to say it, but anything we say about doing a derivative that's not the definition of the derivative is not that, right? I mean, the power rule, the shortcut, I don't care what we want to call it, but what would be, for this problem, what would be f prime of x? By our shortcut, our new power rule. 2x to the first minus 1, right? Because the derivative of this, well, x is just a line, right, with a slope of 1. That's the best way to think about it. Or anytime you just have plain old x, the derivative is going to be whatever number's in front of it, right? So 2x minus 1. And then what can we do to find f prime of 1? Plug a 1 in, right? Now that's going to be the best way, right? Of those 4, that's by far the best way, because number 1, what was wrong with these 2 methods? They were estimates, and this one took a long time, right? Now that's not awful, because it takes a long time. Sometimes that's what you got to do, right? That's what you got to do. And I appreciate the fact that some of you got going through there, and you just said, that's what I got to do, I'm going to do it, right? And that's great. But this one is the best of both worlds. This one is exact, and it's nice and short, right? And so we get both. And so we just plug in a 1, and we get our answer then, right? So that's what we're going to want to do if we can, okay? So, of course, one thing we've got to learn here in practice is how do we work those shortcuts. So that's what 19 and 20 and those problems were supposed to be, was do the shortcut. Like what we did at the end of the period when we went through this table here, right? And we were just doing the shortcut for them. That's what I meant, right? It just said find a formula for f prime. Now, I did mean to tell you to check your answer for reasonableness by comparing graphs of f and f prime. Because we had done that so much in the last chapter, right? We're thinking about card sort of Desmos, f and f prime. So they're saying, okay, here's your f graph, then do your shortcut formula for f prime, and now look at them. And then see if it looks like this would be the derivative of that, right? Because we've done that so much. You could use your calculator, you can do it. It's not a big deal. I'm not worried about that so much. Okay, so let's go. All right, so let's talk about some of those. Let's go through the ones you were supposed to do the long way. The only 2 you were really supposed to do the long way. Because I don't think the book ones ever said the definition of the derivative, did it? I don't think any of the book problems said use the definition of the derivative. Okay. So here's 1 over x, all right? So now, what we were supposed to do here, come on.
Mr. Clark, anything chance you have Patricia Smith?
She's not here today.
All right, thank you.
So, all right, so we're supposed to do this, okay? So, f of x plus h means put an x plus h right there. So I put an x plus h right there, and then put an x right there, so I get this. Okay, now, what you see, this is my former attempt, and this is when I used to resist. I did this a few years back. When I used to resist the bow tie method, but Mrs. Payne finally won me over. And okay, fine, everybody was coming to my class liking to do the bow tie method, so I said, okay, fine. It's fun. Okay, so we start up in the top left, and we get that, and that would be x minus, and then we do this one, and that would be x plus h, like that, and then it's going to be all over that right there. Now, I usually don't distribute that, but you could. It doesn't really matter. Sometimes when you distribute it, you end up pulling it back out. Okay, so, Will, I don't know if you got that far on it. That's what you got to do. You got a bow tie. Whenever we have a fraction, there's three different algebra we're going to have. We're going to have factor and cancel. We're going to have common denominator, the bow tie, and then we're going to have the conjugate method. Those are the three you got to be able to do. Now we got a worksheet that's got some practice on those, and there's some IXLs that have some things on that where we can do it. Okay. So now what's going to happen up here? This is going to be x minus h. So those x's are going to cancel out like that. Okay. I think I've got it down here. Okay. So now I did it again. I did it with common denominator, so it looks a little different. But at the end of the day, you should get down to here. So the x minus x, the x's cancel. The x's cancel, you end up with negative h over this, and then the h on the bottom. So if you flip that up like so, okay, you end up with the h's canceling right here. Okay, these h's will cancel, and so you end up with negative 1 over this. Okay, and now you can put your 0 in for h. Now you can put your 0 in for h. Okay, and now you get, because that's not a problem now, because x plus 0 is just x. X times x is x squared. So now we get that right there. Okay? Now, here's what I wanted to talk about, though. Okay? What's another way? Now, you could just stop right there. I'm fine with that. But what's another way of writing negative 1 over x squared? Right? And think about the original function. The original function f was what? Now, if we were going to use our new fancy shortcut, we can't do our fancy shortcut on this. We have to rewrite that as what? X to the negative first. Now, if we do our fancy shortcut, you bring the negative 1 down in front, you drop the power by 1, which makes it, oh, look at that. Kind of cool how that all works out. How this shortcut, this little shortcut thing, which is so simple, right, ends up coming out of all of that mess, right? Amazing. Okay? All right, so that's that one. Now let's do square root of x. Come on. So square root of x. So this is a conjugate one. And again, the big hint is radical. When you see a radical, I told you that. That's where the conjugate method's going to really work. So you got radical minus a radical. Let's multiply by radical plus a radical. Looks like it's going to be a big mess, but a lot of really good things happen. Because what happens when you FOIL right here? This times this makes what? That times that makes x plus h. The outers and inners are going to drop out because that's what a conjugate does. What about this times this? Minus x, right? Minus x. So look at that. So on top, the x's drop out and you end up with just an h. Well, look at your bottom. Your bottom is going to be these two things multiplied together. Well, what's that mean? The h's will cancel, right? Now I think I've got that. Oops. That's weird. Okay, so I've got my x plus h minus x, but the x's are going to cancel, right? The x's are going to cancel, leaving me just an h, and then the h's cancel, so I end up with just this. Again, that's why I don't want to distribute that stuff out on the bottom. So I just end up with this, end up with a mess of radicals. That's okay, because I can now put a 0 in for h. Put a 0 in for h, I get square root of x plus square root of x, which is just 2 square root of x. Now, you could have, I'm fine if you just stopped right there. Okay, but what's another way to write 1 over 2 square root of x? Could write it like that. And what's another way to write that? Now, I think hopefully you're noticing that since we have this thing called the power rule, which if we have x raised to a power will allow us to do something nice here, that we're going to want to rearrange our things algebraically to look like powers. So we are probably not going to work with radicals very often in here. We're going to want to change those to powers, right? Because powers, we have a nice, neat little rule for powers. So square root of x, we're going to want to turn into x to the 1/2 most of the time. And we're not going to want it to be on the bottom like this. Like in algebra class, a lot of times you were worried about it being a positive power. You wanted to make it be a positive power, which is nice if you're plugging in a number. If I want to plug a number in, if I want to plug like a 9 in here for x, would you rather plug a 9 into this, or would you rather plug a 9 into this? This. So in algebra class, that makes sense. You want to plug a 9 into this, so write it this way. But if you want to do a derivative, which one is nicer? This one's nicer, right? So that's why you need to be able to do this algebra and rewrite things, because depending on what you're doing in the problem, one version might be easier to work with than another, right? So if I want to do a derivative, that would be nicer. Now again, this is the derivative right here. This is f prime. What was our original function f? Which of course is another way of saying x to the 1/2. Well, what's the power rule say about that? You bring the 1/2 down in front, you drop the power by 1, voila, there it is, right? So it's no surprise that we got what we got because we've got this new thing called the power rule, which kind of told us that's what we should end up getting. But I wanted you to go through this because mostly I want you to practice these 3 algebra techniques. I want you to know these. There are some harder algebra techniques we can throw in here. It's just in this day and age with the technology we have and so forth, it's probably not worth spending a ton of time on all this different algebra, but we got a lot of technology that does that for us. But there certainly is some value in doing some of these simpler algebra techniques. All right, so what else on the homework? Anything else? Oh, those shortcuts. So for example, 20. Okay, 19 then should be pretty easy, right, as a shortcut. But on 20, the function was, didn't we have to do 20?
Yeah.
4 square root of x plus 1 over x cubed, right? Well, so that, just rewrite that as 4x to the 1/2 plus x to the -3, right? Now remember, when I do that, that's still f. I haven't done the derivative there, right? That's still f, so your notation is really important here. So I should still be labeling that f. Now, when I want to do the derivative, I label that as f prime. So now I bring the 1/2 down in front, which would be 2x to the -1/2, and then bring the -3 down in front, so that'd be -3x to the -4. So, Jesse, that's all I want, right? That's all I want. So, okay, so there we go. Now, I suppose we could talk about 46 then. 45 and 46. And like it said there, you first, let's do 46. So you would need, it says, find hint, start by rewriting f in a simple form. So at 45, just FOIL it, right? So at 45, just FOIL it out, and then do your power rule. Okay, it would be an easy one. But now, 46 is one I want to talk about. So they give you f of x is equal to square root of x minus 3 over x, right? Now, we're not going to spend a lot of time here in chapter 2 doing these, because that's what chapter 3 is about. Chapter 3 is all about just throwing all of these different types of equations at you. We're going to make up the craziest looking equations, and you're going to have to do the derivative. And we're going to have a big page full of rules that we'll have, okay, not too big, but we're going to have a bunch of rules we're going to have. And you're going to have a test called the gateway test, where you just have to, I give you a page full of 10 of them, I'll give you 10 f equations, and you have to find f prime, okay? And to pass it, you have to get 8 out of 10 right, okay? Now, at some point, you can retake it. Now, I'm going to give you the option to come in and retake it if you don't get 8 out of 10 right, okay? And so if you get 8, 9, or 10 right, you can get like a 100% quiz grade, you know, and if it takes you 2 or 3 times, you can get a 90% test grade or whatever, you know, and then at some point, after a few tries, and you just take the best score you got. If 7 out of 10 is the best you got, then you get a 70% test grade, right? You know, some people might get a 7 out of 10 the first time, and they say, just 10 of them, I'll just say that. I don't know why you do that, but whatever. So you get a chance to just retake it to try to get 8 out of 10 right. Okay, so we're going to spend a lot of time doing that. So right now we're just going to do just some basic ones. So the quiz next week will have a few of these on it, but not a ton, but a few of them. Well, what should we do first on this one? Now, it's funny how everybody says that. By the end of the year, none of you will say that. Okay, a lot of you will say move the x up as -1 and then like distribute it, right? What I would suggest you do is what we talked about with, remember what we talked about the fractions yesterday, how we said 2 plus 3 over 7, you can split that apart. 2 over 7 plus 3 over 7. That's what I'm going to do. Okay, now it's not wrong, move the x up as -1, distribute, but I think what you're going to find over the course of time is with a lot of the things we do, just splitting it apart when you see fractions like this, it's just better. Okay, so that's what I'm going to do. So, and then of course when I see a square root, I've done calculus for so long now, I mean when I see a square root, I just see x to the 1/2, right? Because I know we're doing powers, I want that as a power, right? So when I split this apart, I'm going to write x to the 1/2 over x minus 3 over x. Matter of fact, you should get good enough at this that over time you're just going to, you'll probably do some of that work in your head too. Now notice I'm writing these as f because I haven't changed anything. These are still f. Okay, now what do you do with these powers right here? What do you do with powers when you're dividing? Subtract. So that's x to the -1/2, and then what do we do with this guy? Here we move that x up then. Yeah, here we then move that x up. And so we go to there. Now you would have got the same thing if you did what you said. So it wouldn't be wrong. Move that x up, that's fine. Okay, I just think over time you're going to find out this is maybe a better way to think about it. Okay, doesn't matter. Okay, now we're ready to do the derivative. Some people, they get to this point, they've done all this work and they just think they're done. And you haven't done anything but rearrange it. That's all you've done. This is f, this is f, this is f. Okay, they're just different versions of the same thing. Now we want to do the derivative. So you bring the -1/2 down in front. That'd be x to the what? -3/2. Let's use impropers usually instead of mixed numbers. And then bring this -1 down in front. We'll turn that to a +3, and then it'd be x to the -2 like that, right? And then just leave it like that. Final answers on your derivative. There's no reason. I know in algebra class you had to go back to positive powers or whatever. We're done there. Just stop. Okay? Now, if we had a problem where we wanted to solve or we wanted to plug some numbers into there, like if I want to find the slope at 9, well, now it might be better to then do that, right? Now you might want to drop that down to the bottom so you can plug a 9 in. You might want to go to a positive power, but for this, just stop. Okay? All right. So, next thing, so that's pretty much it, wasn't it, on the homework? Okay? All right. So, I've got some little video things here I want you to see. Oops, that's not it. Okay? I've got a link to this if you want to watch these again on our website. On the website, if you go down here to web links, way down here, that says videos about continuity and limits is the link to this little video here, this page right here. Okay, we're going to watch a couple of these real quick.
Before we get started, we need to answer one question. What is a derivative?
Well, in calculus, the derivative is the slope of the tangent line to a graph. For instance, here's a graph f of x. The point C that I've noted, the tangent to f at x equals c would look like this. In essence, the tangent line is just a line that touches the graph once at that point, sort of like a pencil resting there. Now, a function can have all sorts of different derivatives because, as you progress along a function, you can have all sorts of different tangent lines. Watch as the dot, which represents the x value, travels along the function, and how tangent line changes as the dot moves. We need to figure out a way to determine exactly what the slope of that tangent line is. And we do that using something called the difference quotient.
Okay, this is mostly review. I
In
just
this section, we're going to show you exactly where the difference quotient comes from. Here's a graph called f, with a point on it labeled x. My goal will be to find the slope of the tangent line to f at that point. First things first, the coordinates of this point are x, comma f of x. Now, here's how I get my formula. I'm going to move a small distance to the right of x, and I'm going to call this small distance delta x. It's mathematical language for the change in x. Therefore, this new location is the total distance of x plus delta x from the origin, and this new point has coordinates x plus delta x, comma, f of x plus delta x. Now, if I draw the line that connects these 2 points in red, it's called a secant line. It's not exactly like the tangent line we're looking for that I'm showing in blue, but at least it's a start. I'm going to go ahead and try to find the slope of this secant line. And to do that, I'll use the old formula from algebra, where slope is equal to y2 minus y1 divided by x2 minus x1. And I'll get the slope is f of x plus delta x minus f of x, all divided by the quantity x plus delta x minus x. And if I subtract those x's in the denominator, I get this. Now remember, this is the slope of the secant line, not the tangent line. So I'm not done yet. I need to find a line which is closer to the tangent line than this one. Let's look at that graph again. What happens if I were to make delta x smaller? In other words, my second point will be closer to x than it was before. Now, if I draw the secant line connecting my original point to my new point, which is slightly closer, I will get a secant line which looks more like the tangent line than the previous one did. It's getting closer to it. In fact, the smaller delta x is, the closer this secant line will be to the tangent line. Watch on this animation as the delta x goes from really big to really small. The red secant line comes closer and closer to the blue tangent line. We want delta x to be as small as possible. So therefore, I need to make a small adjustment to my secant slope. Remember, that was f of x plus delta x minus f of x all over delta x. But we want to specifically say that delta x needs to be as small as possible, so those lines basically overlap. And to do that, we'll use a limit. All we do is add in the limit as delta x goes to 0. In other words, I want delta x to become so small, it's almost 0. It can't be 0 because then I would have 0 in the denominator fraction. That's why I have to use a limit. And I say, get that delta x as small as possible. This is the difference quotient. It is the mathematical definition of the derivative.
All right, now, that's nothing new there, but I show that for a couple reasons. You know, if you paid, and I know it was review, and so you may have tuned out a little bit, but he used some words there that are really important, because what we're going to try to do right now is take a little bit of a side trip and talk just about limits. So we've been talking about derivative, the definition of derivative. We came up with this rule for shortcut for derivatives. We've been talking about slope, we've been talking about the chart, all that stuff. Okay, now, what we have just learned over the last couple days, though, is that to be able to make the 2 points become 1, we need this mysterious thing called the limit. And if you heard him talking there, he was saying words like gets closer and closer to 0. But then he said, but it can't be 0 because then you'd be divided by 0. But yet, what do we do at the end of our problem when the h is canceled? What do? We let h be 0, don't we, or delta x. But then I thought we said, well, we can't let h be 0, right? So that's this part of limits. It's kind of confusing. It's my old math teacher, which, again, I have a lot of memories of different math classes I had with him in calculus especially, but in high school. But he used to tell us the limit. He said it was like this. If I said to you when the bell rings to leave the room, you have to get up from where you are and you have to go halfway to the door. And then from there, you have to go half of what's left. And then from there, you have to go half of what's left. And you have to keep doing that. Well, what would be the result? You could never leave, right? You could never leave. And so his line was basically, but with the limit, you can get to the door. You couldn't get to the door without the limit. Half, there'd always be a little bit left, right? There'd always be a little bit left. right? It'd be the point where you wouldn't even be moving anymore, really. But there'd be a little bit left, and you could always go half, and you could always go half, and you could do that forever, right? But the limit would be the door, right? It's what you're approaching. If you could keep going and keep going and keep going, if you could ever get there, the limit would be the door. Well, that's kind of what we're doing here, okay? You can tell where this red line, it's getting closer and closer and closer to the blue line. If it ever actually got there, the formula wouldn't work because you'd be divided by 0. But we can see it through the algebra and stuff. When the h cancels, we can actually put in the 0, and then we can see what it would be if we could get there. Does that make sense? So this idea of a limit is kind of this weird, hard thing to grasp, that it's what it's approaching. And you can see I had this up here on this other screen. Let me bring that back up. And so, I don't know if you want to write that down, that probably doesn't really matter. But the limit, so the derivative rule, the derivative definition needs this thing called the limit. But there are limits that don't have anything to do with derivatives. Limit is a mathematical idea. We need it here for this, but we can use, limit shows up a lot of other places too. Limits, so we can do limit problems. So that's what we're going to do for a day or two here, is we're just going to talk about limit problems. Now, every once in a while, we'll connect them back to derivatives. We'll say, oh, hey, wait a minute, this limit problem looks like that. So, oh, this is also not only a limit problem, but it's the definition of the derivative problem too. But some limits don't look anything like a derivative, and they don't have anything to do with a derivative. They're just a limit problem, okay? They're just a limit problem. Okay, so what this says is the limit of f of x as x approaches a equals L, okay? It's like saying, what are the outputs getting close to as the inputs get closer and closer to A, right? The word approaches is used a lot. Okay, so what are they getting closer and closer to? Do they ever equal that? Well, in a sense, yeah. I mean, like say when we cancel some stuff and we can actually plug in an A, we can actually plug in that number and see what it is, okay, we can do that. All right, so that's kind of what is going on here with when we talk about limits, okay? So I'll introduce this here just a little bit, and now I'm going to show you some more videos, and they're going to talk about this. So for example, so if you wanted to write something in your notes, maybe this problem wouldn't be bad. Right here. So here's an example of just a plain old limit problem. This doesn't have anything to do with derivative, doesn't have anything to do with slope, right? Doesn't have anything to do with it. This is kind of a little side trip here now. We're going to investigate limits because, geez, if they're so important, if we can't do the derivative without limits, I mean, we can because we have these shortcuts, but remember, where did those shortcuts come from? That definition right there, right? We did x squared, we did x cubed. They came from here, right? So technically, we can't do derivatives without the limit. We can't let the 2 points become 1 without limit as h goes to 0, right? So if limits are so important, we better know a little something about it, right? So that's why this little side trip. So that's what section 2.3 is about. So here's a parabola. So as x is getting closer and closer to 2, what are the y values doing? Getting closer and closer to 5, aren't they? Now, when we talk about limits, we actually have to talk about from both directions. What about when x approaches 2 from this side? What are the y values doing? Getting closer and closer to 5. One of the things we will do on our calculators is we will look at a table of values. Here's where a table of values can come in really handy. And we're not going to do the calculator tables today. We're going to do that on Monday. But if I go on to my calculator, I can do this real handily here. I can just go into my graph screen. I can put in x squared plus 1. I can do this. I can hit Control T as a shortcut to give me a table. It's kind of a split screen. I tell you what, I'm not going to do a split screen. I'm just going to go to the table. So I'm going to go to Menu. I'm going to go to Table. Maybe that's the only way I can do it is a split screen. I didn't think. Oh, it doesn't matter. Okay, and I want to do this as, what was I saying, as x approaches 2, right? except now I want to go to my table settings. I'm going to go to my table settings, and I'm going to change this number right here to 0.001 because I want to get really close in my table. Okay, oh shoot, so now I'm going to go, okay, back to the menu, and my table start, I want to start my table right at 2. Okay, so now, let me up arrow. So look at that table. So can't you tell from the table what's happening, right? Now, you might be focused on this line, but really I don't even care about this line, right? Because the limit is what it's approaching, right? What is it approaching? These y values are clearly getting closer to 5. If I could see more of these y values are clearly getting closer to 5, right? And so what I can see in that table that, yeah, the limit is 5. Okay, now, back to this. You look at that and you say, well, duh, I just put a 2 right in there, right? 2 squared plus, that's right. We will always do that first. The first step we will ever do in doing a limit problem is we'll just try to plug it in. Maybe it'll work, right? A lot of times it will. So on one like this, we just plug in a 2. Okay, now what about this one? Now I've included the graph just so you can see. Okay, I've included the graph so you can see it, but on a lot of these problems, we're not going to give you a graph. Okay, well, if the first thing we often do is plug in a 3, go ahead and plug in a 3. What do you get? Undefined. Oh, okay, so that's no good. Well, this is what this graph looks like. Because what happens if you do x plus 3, x minus 3, if you do this to this problem, and you, right, cancel those, then you get x plus 3. So this is just the line x plus 3 is all it is, except it's got a hole at 3. Okay, well, that's what happens when you get 0 divided by 0. I think I've talked about that before. And we're going to talk a lot more about that on Monday. You get 0 divided by 0. That's usually a hole in the graph. Well, now, as x gets closer to 3 from both sides, what are the y values doing? No. What are the y values doing? They're getting closer and closer to what? They're getting closer and closer to 6, right? Or do they ever equal 6? No, but what's the limit? 6. The limit is 6. The limit, don't forget, the limit is what are they approaching? Even if they never get to 6, the limit is still 6, because that's what the y values are approaching. Same thing here. The y values are approaching 5. Would they ever get there? Yeah, they did. But that doesn't matter for the limit. It's what are they approaching? They're approaching 6. Now, the way we would work with algebra, let's pretend we didn't have the graph. We would just factor, we'd cancel, and then we'd plug in our 3, right? Just like our h. We get to the end, we do some canceling, then it's okay to plug in the 0. Well, same thing here. We do some canceling, now we can plug in our 3. 3 plus 3 is 6. And that's how we get it, right? But graphically, it's easy to see what's happening too. Okay? And if I did that on my calculator, if I went back to this problem, and I put in, I think it's control. What did I say it was? Control G. Control G opens this. So would tab, though. I could have done that. And then Control T gives me a table. So if I wanted to do this problem that I just did a minute ago, if I wanted to put this problem in and go x squared minus 9, and then down here put, what was it, x minus 3. If I want to put that in there and then come over here to my table, let me tab. Oh, not tab. I got to highlight my table. There we go. Now I go to my table and go to my menu options. Okay, now let's start my table here at 3 this time because we're doing x approaches 3. So now see what happens here? So what's happening right at 3? It's undefined. But see, we don't care about that. We want to know as x is approaching 3. So as x is approaching 3 from both sides, what are the y's doing? They're getting closer to 6, right? We can tell from both sides the y values are getting closer and closer to 6. So the limit is 6. So when we do some calculator ones, you're going to literally write down this table as your proof that the limit is 6 because the y values are approaching 6, okay? So, like I said, it's this weird kind of thing where, you want x to get to 3. It doesn't have to get to 3. It's what are the y values approaching as it gets to 3. You might be able to do some algebra where you could then plug in a 3 eventually, but maybe not. Sometimes you can just plug a 3 in right away, and it works because it might be just a real simple one like this one. You just plug in a 2, and you get 5, and you're done, right? I mean, so that's what limits are about. Okay, so let's they've got some really nice little videos here, and he's got some kind of funny little ways of thinking about it that I think are kind of nice.
You may have heard a lot of talk about limits, but the plain fact remains, most people don't understand what a limit is. So for now, we're going to focus on what is a limit. In basic terms, a limit is a height that a function intends to reach. That's pretty important, so let's say it one more time. A limit is the intended height of a
I
function.
like that term.
Now, this might give you pause. You might think, how am I supposed to know what height a function intends to reach? I don't even know what my intentions are most of the time. How am I supposed to discern the intentions of a function? That's a good question.
Like that last
And
part,
the fact
it
that
looked
you
like
don't
he wanted to
understand
get the
exactly what I'm
sense.
talking about is because all of the functions you've been dealing with, or at least most of them, have had their intentions completely clear. If a function intends to reach 3, it reaches 3. If a function intends to go 6 units high, it goes 6 units high. There hasn't been a lot of mystery so far. So I understand that you might be a little confused, but you've dealt with function heights a lot. So we might as well review function heights a little bit, and then get into exactly what I mean by intending to go to a certain height.
Okay. So what would be a function? Could you think of a function that wouldn't know what it intends to reach? I mean, we saw the one with a hole. So it wanted to get to 6, even though it couldn't because of the hole. What would a function that we've seen that where the limit would not exist mean? Where it doesn't, at a certain point, you can't tell from the graph what it's trying to get to. We've had a couple different examples. What would the graph have to look like where you would have no way of telling at 2 what it was trying to do? What y value it wanted to be at? What y value is that graph trying to reach? Well, it is reaching that one, but down here, is it intending to reach that one on the left side, or the y values approaching this point? These y values seem to want to go to here, right? These y values seem to want to go to here. Okay? That's what we're talking about, because again, it's not about what y value does it have, it's about what y value is it getting close to, what y value is it approaching, what y value does it intend to get to, okay? That's the difference.
By definition, a very simple function graph. What I have here is the function f of x equals x squared, basic parabola. You'll notice that the function changes heights all throughout its domain. That's a very fancy way of saying that the function reaches many different heights based on whatever the x value you're looking at happens to be. For example, what if I look at the function height that corresponds to x equals 2? Well, it's not very difficult to figure out exactly how high that function is going to be when x equals 2, because all I have to do is plug in that x value into the function to figure out what that height will be. So, if I plug 2 into x squared, I get 2 squared, or 4. This means that the function reaches a height of 4 whenever x equals 2. Pretty simple. But now I can create my first very basic limit statement, and that is the limit as x approaches 2 of f of x equals 4. This just means that whenever I'm getting very close to the x value of 2, my function is getting very close to the height of 4.
Okay, very simple. Simple, basic, nice continuous graphs. The limit is very basic. It's just what it seems to be. It's
There's
basic.
something really earth-shattering about what we just learned. But that changes when we examine functions that do not reach the heights they intend. Take, for example, this function. G of x equals the fraction x squared minus 6x plus 8 divided by the quantity x minus 2. Here's what the graph looks like. It looks like a plain old line. Or does it? If we zoom in, you'll see that it has a hole in it at the coordinates 2, -2. The hole exists because plugging x equals 2 into the function results in 0 divided by 0. And we know that dividing by 0 is a very bad idea. It breaks mathematical laws that we really can't even get into here. However, though this graph has a hole in it, it still possesses a limit when x equals 2. Clearly, the graph intends to reach a height of -2 when x equals 2. Even though that graph doesn't actually reach that height, it doesn't matter. The limit still exists, and we can say that the limit as x approaches 2 of g of x is equal to -2. This begs the question, when exactly does the limit exist? We examine that in the next module.
So that's what we'll talk about here. Here the limit doesn't exist. So Max, that's perfectly normal to think, well, it'd be this top one, because that's where it's filled in. That's what the function value is. So there's a difference between the function's value, y value, and what the limit is. Now they're closely connected, and many times they're the same. Many times the limit and the function value are the same. That's why the first thing we do is plug in the 2, see what the y value is, because many times that is the answer. Okay, and for normal equations, you do that, you get an answer, that's going to be it. Okay, so many times that's right. So to be honest, we don't spend much time working with those because they're so simple. All you do is plug in 2, you get a y value. So we start looking at the ones where something weird is happening, where like a hole, or maybe something like this, right? And so it comes back to here, the function's y value is not the same thing as what its limit is, okay? The actual y value is not the same thing as that, okay? So now we got 2 more.
So that doesn't have a limit, that graph?
That, it's going to turn out that one does not. That's what he's going to talk about here.
Of what a limit is, and we need to talk about.
This is my favorite one. This is one I'll use
To
the
illustrate my
reference
point
line.
before we get started, let's set up an example. Let's say you and a friend are going to meet for dinner, and you're meeting at a diner that's centrally located between the two of you. If you live east of the diner, and your friend lives west of the diner, and you both want to drive to meet there, ideally, the roads which lead to the diner will lead you to the same place. If you travel towards the diner from the right, or east, and they travel towards the diner from the left, you should meet up in the same place. Mathematically, this is basically what a limit is. A limit exists if you travel along a function from the left side and from the right side towards some specific value of x. As long as that function meets in the middle, as long as you arrive at the diner, as long as the heights from the right and the left are the same, then the limit exists.
That's really important where you talk about from the right and the left, just like that example I have up on the board.
Now it's time to get down to the brass tacks and look at this mathematically. Take a look at the graph of this function f of x. Visually, you can see that it's got a break in it at x equals 4. So, if we travel towards 4 from the right, we will arrive at a height of 2. However, if you travel towards 4 from the left, you will arrive at a height of 1. This means that no limit exists for f at x equals 4. Let's go back to our diner metaphor for just a second. Notice that as I'm traveling along the road from the right, I end up at a height of 2. But if you travel along the road from the left, you end up at a height of 1. These heights don't match. We won't both arrive at the diner, and no limit exists. We call the heights at which we arrive from the right the right-hand limit of f of x, as x approaches 4 from the right. And we denote this with a little plus sign in our limit symbol. Our height that we arrive at from the left is called the left-hand limit of f of x, as x approaches 4, and it is denoted with a little negative symbol. Mathematically, in order for a limit to exist, both the right and the left-hand limits must be equal.
And if you want to jot that down in a little bit, so there's the key. The y value is one thing. If I ask you on this problem, if I ask you what is f of 2, you're talking about this y value right here, whatever it is, because that's where it's filled in. So the y value, and you can't have both these filled in, because then it wouldn't be a function, right? It wouldn't pass the vertical line test. So one of these is filled in, f of 2 would be that y value, but the limit at 2 would not exist. Now, notice then he talked about a left hand and a right hand limit. those will always exist. The left and the right-hand limit will be something, because the car on the left intends to get somewhere. In this case, the car on the left intends to get here. So that's the left-hand limit. And the car on the right intends to get here. And that's the right-hand limit. If those two aren't the same, then the limit at 2 doesn't exist. You got 2 from the left, 2 from the right. If those are the same, then that's the limit at 2. If they're not the same, then the limit does not exist. Okay? So from the left and the right have to be the same. In other words, the cars have to meet. You'll hear me say that a lot. If the limit exists, then it's the place where the cars meet. Where the cars meet is where the limit is. Okay? All right? So if they don't meet, limit doesn't exist. All right? So they're gonna continue that metaphor here a little bit, which is, I think, is helpful. But it's different than what the y
function just a little bit. This new function, we'll call g of x, does possess a limit. Can you see why that's the case? It's because the function no longer has a break at 4. Now, there's something to be said here. The previous function did not have a limit at 4. It did have a limit at many other points. For example, a limit existed at 1, at 2, at 5, at 0. All these x values showed locations where the graph did not break. In essence, a graph will not possess a limit if it breaks at the given x value. That's why our new function does possess a limit at x equals 4. Now, let's go back to our diner example one last time. Let's say we're traveling towards the diner. We both arrive at the same location, but the diner isn't there. Maybe it's caught fire or something. Does that mean the limit doesn't exist? The truth is, the limit will exist even if the diner's not there, because you still arrive at the same place. In other words, mathematically, a limit can still exist if your destination is a hole in the middle, because it doesn't matter whether or not the point is actually there. What matters is that you arrived at that point, coming from the right side and the left side. In conclusion, a limit exists on a graph if you arrive at the same height coming from both the right and the left side of the given x value.
See, it's kind of like, you see, I like that with the diner burned down. I like it with the cars, right? It doesn't matter if the diner's still there. They both arrived there, right? There's nothing there, but they both got there. That's their intended destination. That is the limit. So to continue that metaphor, the diner burned down. They rebuilt it in a new place. This guy goes to the old diner. This guy goes to the new diner, right? The limit doesn't exist. They did not meet at the same place. They did not meet there. The limit does not exist. Okay. Now, before we do this last one, there are some IXLs. Now we'll do these later. But I just want to talk about this a little bit because you're going to have some homework problems that are going to be similar to this. Okay. So on this one, it says use a graph to find the limit. So what's the limit as x approaches -6? What do you suppose I would put in here? -4. Okay? How about this one? As x approaches -4. 5. Even though there's a hole there, we don't care. Right? What about as x approaches -9? Which is over here. That's also -9, right? I mean, it's very simple when you understand the concept. As x approaches 1? 6. Okay, so a bunch of these are kind of the same kind of thing. So, okay, here's one with that break we were talking about. What about when x approaches 9, it says? Aha, they tried to fool you, right? They put this break over here at 6, but they ask about 9. So, and I think he might have mentioned that. Did he say there's a lot of other places where it exists? But at this place at 6, it does not exist. The cars don't meet. Okay, so the limit does not exist here, but at 9 it does, right? It's right there. Okay, so you're going to have some of those just with graphs, and here's one, right? There's 2 places here where the limit doesn't exist. The limit's not going to exist there. The limit's not going to exist here, but here it would, and of course all these other places it would too. Okay, all right. So anyway, that's the idea there. So now, so graphically, that's not too tough. Okay, where does the limit exist? I mean, once you get that concept, right, where the cars meet, it's where the cars meet. Now, what the hard part, the part we want to focus on from here on out today, and so some of your homework is going to be some of these graphical examples of these limits, and then what about where you don't have a calculator, you don't have a graph, all you have is an equation, right? So I think visually, if you can see the graph, limits are pretty easy. You picture the cars being. Okay, if you don't have a calculator and all you can do is algebra with it, and you can't see the graph, well, that's when we come back to, that's what they're going to talk about now. Okay, but we've already done a little bit of that today.
You can determine whether or not a limit exists. The next logical step is to try to figure out what the heck that limit is. So that's what we'll be focusing on in this section. How do you find a limit? The fancy word for finding the value of a limit is evaluate. So when you see the direction evaluate, basically you should be expecting to get a numerical answer. There are three major ways to evaluate a limit. They are substitution, factoring, and the conjugate method.
They left off our bow tie,
We're going
which we're going to have to
the
do too.
easiest one, which is direct substitution. It is just as easy as it sounds. We'll take an example. Here's one. The limit as x approaches 0 of the fraction x squared minus 1 divided by the quantity 2x plus 3. In order to evaluate this limit, all you've got to do is plug in 0 everywhere you see an x. So we'll put in 0 in the numerator and in the denominator, and we end up getting negative 1 divided by 3. So our limit is negative 1/3. It's as easy as that.
Okay, now, if you were to graph this, it would have something weird happening at negative 3/2, right? Because at negative 3/2, what would be going on? This would be 0 on the bottom, right? Be undefined. So this graph's going to have some kind of weird, maybe an asymptote, vertical asymptote, right? We haven't talked about asymptotes at all because it's going to be a later chapter. We're going to talk about infinity. We're going to talk about, what happens to a graph. What do you talk about here with limits? If you got a graph doing this, well, clearly this car is going way up here. This car is going way down here. They're not meeting. Even if you got a car doing that. Right? They're not meeting. This one's on this side, this one's on that side. I mean, you could say they're both going to infinity, I guess, but that's not a number. So we would still really say this does not exist, but we'd say going to infinity. But that's chapter 4. We're going to talk more about that. But something weird is happening there, probably vertical asymptote. So the limit would not exist there because the cars aren't meeting. But we didn't ask about negative 3/2. We talked about it 0, right? And so that might be like on this part of the graph, right? Where the limit, where it does meet. So first thing we always do is substitute, right? The first thing we always do is we plug in this case, a 0, and then we see if we get a number. And for the ones we're going to be doing, if we plug in and we get a number, you're done. That's the answer. That's the answer. Even if we don't know what the picture looks like, we'll just.
Unfortunately, not all
that's the
limits
answer.
are this easy. You've already seen one for which that's the case. Remember that function we were dealing with in the first section of this chapter? Maybe if you don't, here it is again. The limit as x approaches 2 of the fraction x squared minus 6x plus 8, all divided by the quantity x minus 2. We looked at this before. It had a hole in it at the coordinate 2, negative 2. And we concluded from that the intended height was negative 2, making it the limit. However, it would be nice to be able to figure out why this is true mathematically. To do that, we'll have to use the factoring method. As you can see, and as we saw before, direct substitution results in 0 divided by 0, which is not allowed. We'll have to resort to this new method. We'll use the factoring method because the numerator of this fraction is factorable. If we factor it, we'll get x minus 4 times x minus 2. Can you see why that's a good idea? Well, the reason is because now the numerator and the denominator both contain the term x minus 2, which I'm going to cancel out. This leaves the limit at x equals 2 of x minus 4. This is much simpler to solve because now you can use substitution. And when I do, I get 2 minus 4, which is equal to negative 2. Remember, we use the limit that's going to be negative 2, and we're right. Feels good to be right. If the substitution method fails and the factoring method fails, you're not without hope. You can still try the conjugate method. Before we talk about the conjugate method, though, you might as well figure out what a conjugate is first. Take a look at this expression. The square root of x minus 4. Now, this is a plain old two-term expression. However, it is easy to make a conjugate. All you do is change the negative sign in the middle to a positive sign. The conjugate of the square root of x minus 4 is the square root of x plus 4. That's all there is to it. Now, what if you see an expression like this in a limit problem? For example, this limit problem. The limit as x approaches 16 of the fraction, the square root of x minus 4 divided by the quantity x minus 16. Well, what we'll do is multiply the top and the bottom of the fraction.
Because if you
by
plug a 16 in,
of the radical
you get
expression,
0 divided by 0.
which, as we said, was the square root of x plus 4. Now, the magic of this is that as you multiply out, the numerator will actually become x minus 16. You don't want to multiply the denominator out. Leave them as separate factors. Since I have x minus 16 in both the numerator and denominator, I can cancel them, just like I cancel like terms in the factoring method, and I'm left with the limit as x approaches 16 of 1 divided by square root of x plus 4. Do you see why we didn't want to multiply out the bottom? It makes simplification much easier. Now I'm able to plug in 16. Substitution works. When I do so, I get 1 divided by 8. So the limit as x approaches 16 of my original function is 1/8. And that's the conjugate method.
Okay, now, sometimes something that happens in those problems, now let me do it so the video shows this. Sometimes what happens when you do this, there's a little algebra thing that we sometimes struggle with. Let me show you this, is that what if the top, when he factored that, or when he FOILed that out, would have been this, and then the bottom would have been x minus 16, and then whatever he had, what was it, square root of x plus 4. Okay, what would have happened right there? Can you cancel those? Well, the answer is no, they're not the same, but they're really close. What can you do right up here? If you factor out a -1, now, where people get confused, some people think if you factor out a -1, you can turn that into that. That never works. You can never turn x plus 16 into x minus 16. You can't do it. But think of it this way. What's 4 minus 9? What's 9 minus 4? When you flip around a subtraction, all you're doing is making it opposite. So by taking out a -1, what you're doing is flipping it around like that. Or just think of it this way. If you take out a -1, the 16 turns negative, the x turns positive, and of course then you can flip that into x minus 16, right? But anytime you flip around a subtraction, you're just making it opposite. So you can take out an opposite here, okay, like this, and then your x minus 16s can cancel, okay? So if you ever see a situation like that, which happens from time to time, you can cancel those, by just doing a little piece of algebra. Okay.
There you have it. There are 3 major methods to evaluating a limit. Substitution, which is the easiest. Factoring, which is useful when either the top or the bottom of the fraction is factorable. And the conjugate method, which is useful for radical fractions.
Okay, and then I would add to that list the common denominator, the bow tie, okay, is another one that we have that is a good one, okay? All right, so, wrapping this up then, okay, that's back there, so. All right, so algebra. So let me see, check on the IXL, what that is next. Okay. We go back to here. We go back to our calculus topics. There's one in here where, yeah, this gets into some of those kinds of situations. So right here we got one where you would just FOIL this out. You just FOIL this out, some nice things are going to happen, and you can do some canceling, you can get answers. So there's going to be I wouldn't do these yet, I don't think. I think we got plenty to work on here with our homework in the book and our worksheet here. But I might throw those out there, next week as we get ready for Wednesday's quiz. We got some other stuff we'll be doing with the calculator. So I might throw them out here since you have the weekend. If you want to work on these algebra ones, it might not hurt. So I'll write those down. What was that? That was F6. These are some pretty simple ones. These are just plugging in this F5 and F6. So I'll throw those up here as kind of optional things. The graphing ones are pretty simple as well, E1. There's some one-sided, I'll maybe put those up here a little later. Let me see, those are infinity, so we don't need any of those things. Okay. All right, so I think that's probably all we need for this. So I'm going to change on your homework sheet a little bit here because this homework sheet was kind of based on us getting to section 2.4 before Thanksgiving, which we're not going to do because of our kind of honked up schedule this year. So we're going to go 2.3, and we're going to do, I guess I do have it written down there. I said something about doing them in class, but we're not going to do that. You'll just go before it. So it's basically those problems. So it's essentially those problems that are on there. And then we're going to do this. I guess this one is pretty much what I had written on there. So I'm going to give you this worksheet that's got what I call them algebra limits, because you're just going to do what we saw there at the end, which was the and I'm going to be putting up some optional IXLs here. This is, of course, under calculus from time to time over the next couple days. So I guess E1, F5, and F6. Now, there's certainly no hurry to work on these, okay? Because you can, next week, you may be looking to come back and do some review on some of this, and so you might want to do those then, or do a few of them now, get up to a score, do some of the simpler ones, and do some of the other ones later, okay? But I would say that would be what we work on here. So let me give you this worksheet. All right, so you got your bookwork and then the worksheet and then optional actions. Factor, conjugate, bow tie. Factors just, work it out, FOIL it out, whatever, something cancels. In all of them, something cancels, eventually. But, there's never a problem where you have like two options, right? There's only one way it's going to work. If you have a radical, big hint, if there's a radical, it's going to be the conjugate.
Yeah.
Okay? If there's a radical, it's going to be a conjugate. If there's fractions like number 7, then it's going to be the bow tie.
What about like number 1 on the worksheet?
That's factor. Well, the first thing you do is substitute.
Yeah,
The
but
first thing you always do is plug in,
you would get
in this case, a 2. Right, so now you try to factor. You try to FOIL that top.
2.
Yes.
If T, since 2 doesn't work, you factor that doesn't work. So,
Okay.
no, then you get x plus 2 over x.
Right.
The line is
Right. But what they're saying is after you do it, then when you plug in,
you cancel the x minus 1.
yeah, so now you plug in your -1, and what do you get?
So you gotta do the conjugate, but which one do you do the conjugate?
No, you don't do conjugate. No.
That's what you,
Radical, just do the conjugates is there for radical, okay? So if you plug in, for right now, if you plug in and you get this, okay? Let's just say this right here, okay? Let's make this easy for right now because we'll get into this later. We'll talk more about it Monday. If you have 0 divided by 0, keep going, right? Because on number 2, when you put a -1 in first, what do you get? What did you get when you put -1 in first?
you get 0
And you get something else on the top, right? So actually on that one, you probably could have just said undefined right away. Now, you wouldn't say undefined, you'd say does not exist. And we'll talk more about that next week. But it's undefined, you get undefined. But let's say you went ahead and factored it. Okay, but if you get, so what happened on number 1 when you plugged into 2? You got 0 over 0, right? So when you get 0 over 0, you keep going because you got an answer on number 1, right? You ended up, did you get that factored?
Yeah.
Number 1? Okay. So you keep going because you might get an answer. But if you get 3 over 0, or 7 over 0, or -2 over 0, right? In other words, if you get k over 0, where k is not a 0, right? You get some other number over 0. Then you say does not exist. Now, we'll talk more later about how we want to investigate that further. But for right now, we just do that. So if you get 0 over 0, you keep going because there may be an answer. If you get another number over 0, you just say does not exist. And because basically what's happening is you have a vertical asymptote. Okay? And so the cars don't mean limit doesn't exist.